Hello and welcome you all to the 12th lecture of the NPTEL course on Electroweak interactions on standard model of particle physics. So far we have been looking into the Dirac equations and its solutions, and in the last class we introduced some very interesting properties which are called the helicity, and we argued that the helicity, which is basically the spin projecting along the direction of its motion, and it once again has eigenstates like it shares a eigenstate with the Dirac Hamiltonian because it commutes with it, and then we found actually basically the eigenstates, and the eigenvalues are once again plus half and minus half, which says that either it can be projected along the direction of the motion or opposite to that, and that is what we called a right helicity and the left helicity, or we denoted with u up or u down for the particle spinors, and similarly for the antiparticles we actually found those solutions. Now today we are actually going to discuss something interesting, and this is what is called the chirality. Now let us go to the definition and let us get started. All right. So you remember that the very important part of actually constructing the Dirac equation was the invention or the introduction of what you call the Dirac matrices, which are called the gamma mu's. Now these are the 4 cross 4 matrices, and mu actually takes values from 0, 1, 2, 3. So there are 4 matrices of this kind: gamma 0, gamma 1, gamma 2, gamma 3, and there is a very important algebra between the gamma matrices which is there, which is basically the anti-commutation of gamma mu and gamma nu to give you 2g mu nu, right. So this is something that we already know of. Now what we are going to do, that we are going to define a new gamma matrix, and that is what we call gamma 5, and the definition of gamma 5 is I gamma 0, gamma 1, gamma 2, gamma 3, or you can also write it in terms of this expression like minus I by 4 factorial epsilon mu nu rho sigma gamma mu, gamma nu, gamma rho and gamma sigma. Okay, and this epsilon mu nu rho sigma is what you call a completely antisymmetric tensor of rank 4. That basically means that here, like for example epsilon 0, 1, 2, 3, epsilon in the cyclid coordination of 0, 1, 2, 3, these are going to give you 1, and anything which is non-cyclic, that is going to give you minus 1, and any indices which are being repeated, that will give you 0. So this is the properties of what you call the antisymmetric tensors. Okay, so this is, say for example 1 epsilon 1, 1, 1, 1, for example, that is equal to 0, and so on and so forth. But with this definition of gamma 5, like I gamma 0, gamma 1, gamma 2, gamma 3, what we can find out that there are some interesting properties of this gamma 5 matrix, which is going to be very useful in defining something which is called chirality. First of all, gamma 5 dagger is going to be equal to gamma 5. Gamma 5 square, if you do that, that is going to be equal to 1, and gamma 5 gamma mu, if you take that anti-commutation, that is going to be equal to 0. Okay. So now we can also explicitly check, do this matrix multiplication back home, like do the matrix multiplication, take our values of gamma 0, gamma 1, gamma 2, gamma 3 in the Dirac-Pauli representation, and do this matrix multiplication to show that actually in the representation that we are using, this actually takes the form like 0 0 1 0 0 0 0 1 1 0 0 0 0 1 0 0. What does it mean? This basically means that this is actually representing like identity matrices sitting in the non-diagonal entries. These are 2 cross 2 identity matrices, right. All right. So these are some of the properties of the gamma 5 once we have defined it in this way. Now why exactly this is interesting, where exactly this is going to be required, that is the question that we are going to ask. First, let us once again remind ourselves of the helicity eigenstates that we found out. So, u up was this normalization constant which I am not going to get bothered with. C stands for cos of theta by 2, S stands for sine of theta by 2 and e to the power I phi, and so this is u up, u down, v up and v down, where you see this S and C is essentially C is cos theta by 2, S is sine theta by 2. This up basically means H equal to plus half, and down that basically means H is equal to minus half. So, these are helicity up and helicity down, or helicity right helicity left helicity, whatever notation that you want to do that. So, this is something that we solved in details. Now, I am interested in looking into this form of the spinors in what we call the ultra relativistic limit, where the energy is way greater than the mass, or I can then simply say that E square equal to P square plus M square. So, if E is way larger than the mass, so then E essentially is E square equal to P square, or rather E is almost equal to P, which basically means that this ratio which is kind of sitting here in these expressions of the spinors, that simply goes to 1. So, this is the ultra relativistic limit. This is also, you can say, this is applicable to those massless particles if you wish, right. So, in this limit, how exactly the spinors look like? Let us write them down. So, this is C S e to the power I phi, this is C S e to the power I phi, this is for u up. What about the u down? This is minus S. Once again, to remind you, this S stands for sine theta by 2, C stands for cos theta by 2, right. So, this is minus S C e to the power I phi, and then P by E plus E m becomes 1, this is S, and this becomes minus C e to the power I phi. What about V up? So, this is S, this is minus C e to the power I phi, and then this is minus S once more, and this is C e to the power I phi. What about the V down? I am not bothered about the normalization constant which I am not writing. So, once again, this is, if you take this limit, this is C, this is S e to the power I phi, this is C, this is S e to the power I phi, right. So, with this, now what I am interested in, that I am interested to operate gamma 5 on this u up. So, gamma 5 in, once again, the Dirac-Pauli representation is this matrix, this 4 cross 4 matrix, and I am operating on this C S e to the power I phi, C S e to the, do this matrix multiplication. So, this is 0 into blah, 0 into this, 1 into this. So, this entry is C. What happens to the second one? 0 this, 0 this, 0 this, and 1 into this. So, this is S e to the power I phi. So, the next one, this is actually C, and the next one is S e to the power I phi. So, what exactly this is giving? This is giving you back essentially the u up, correct? So, this is plus u up. That basically means that u up in the ultra relativistic limit is an eigenstate of gamma 5, and this is not only true for u up, but this is true for all the others u down, v up and v down, and you can calculate that for u down this is minus u down, that is the eigenvalue is minus 1, for v up this is reverse minus v up, and gamma 5 v down is plus v down. So, this is exactly the point, that you know, in the ultra relativistic limit, the helicity eigenstates are also the eigenstates of gamma 5, right. So, in general, the definition of eigenstates of gamma 5 are defined as the chiral states, but what we have seen is that the helicity eigenstates in the ultra relativistic limit are also the eigenstates of gamma 5. So, therefore, there is a equality of the helicity eigenstate and chiral eigenstates in the ultra relativistic limit, or in the massless limit you can say that the helicity eigenstates are essentially the chiral eigenstate. Now, what is the definition of the chiral eigenstate? So, the way that we defined is as follows, that gamma 5 acting on UR, we say that is going to give you UR. So, once again the right R stands for this right-handedness, L stands for the left-handedness, okay, left-handed chiral states, right-handed chiral states. So, this is how we actually say. So, we say that gamma 5 UR is plus UR, and then gamma 5 UL, the left-handed one, will actually pick up a sign, and that will be equal to minus UL. This is like the spin projecting opposite to the direction of the motion. You can visualize that helicity eigenstate thing. So, gamma 5 VR, because this is acting for the anti-particle, for the right-handed this will pick up a sign, and for the left-handed this will not pick up a sign. So, this will remain plus VL. So, this is exactly how we define the chiral eigenstates, which are basically the eigenstates of gamma 5. Now, why do we do that? Because this is closely resembling that of the helicity eigenstates, and precisely to say these are the helicity eigenstates in the massless or in the ultra relativistic limit. So, this is precisely what we have said, that U up is UR when E much greater than M, U down, U is therefore UL in ultra relativistic limit. Similarly, V up resembles with VR, and V down resembles with VL in the ultra relativistic limit, or in a sense helicity eigenstates are the chiral eigenstates. So, this is something that we have already obtained. Now, how do I essentially define? So, this definition is good, that the way that we have defined UR, UL, VR and VL as eigenstates of gamma 5, but can I sort of obtain this using some chiral projection operators, and this is what I am going to define now. Suppose I define PR is equal to half into 1 plus gamma 5 as a projection operator, and PL as 1 minus half into 1 minus gamma 5, so that PR plus PL is actually equal to 1. Now, you have to remember that gamma 5 is a 4 cross 4 matrix. So, you cannot be added to a number 1. So, this 1 plus gamma 5 is essentially 1 is the identity 4 cross 4 matrix. So, PR and PL, these are projection operators on matrices of dimension 4 cross 4. So, these are all 4 cross 4 matrices that we are talking about. So, now why should I call this to be projection operators? Because they have some typical properties. What kind of properties? For example, first I take PR square, which will be half of 1 plus gamma 5 square, and this will be 1 by 4 1 plus gamma 5 square plus 2 gamma 5, right, and then this will be gamma 5 square is equal to 1. That 1 is also not 1, it is the identity matrix 4 cross 4 identity matrix, but whatever. So, this is 2 plus 2 gamma 5, the 2 gets out and gets cancelled, and this is half into 1 plus gamma 5. This is turning out to be PR. So, PR square is essentially PR. Similarly, you can show that PL square is equal to PL. So, that is something that you can do very easily. So, this is something that you should explicitly check using the properties of the gamma 5, and then let us take PRPL together. So, what happens that if you take PRPL, this is half into 1 plus gamma 5 into half into 1 minus gamma 5, and what happens in the multiplication, we know that this is going to become 1 minus gamma 5 squared, and just because gamma 5 square equal to 1, this actually goes to 0, right. So, PRPL goes to 0. Now, let us try to see if we can bifurcate the Dirac spin or U into UR plus UL. So, let us do that, and where I define UR is simply the projection operator PR acting on the spin or U, and UL is defined as a projection operator PL acting on U to give you UL. So, and also this point that just because PR plus PL is equal to 1, it is easily identified that you can always write U is equal to UR plus UL. Is this point clear? So, that basically means that you can always bifurcate the spinor into right chiral projection plus left chiral projection, where right chiral projection is defined by half into 1 plus gamma 5 u, and the left chiral projection is defined like half into 1 minus gamma 5 u, or in a sense you can say PRU and PLU in our language. And you can quickly check that UR plus UL, which is half into 1 plus gamma 5 u plus half into 1 plus 1 minus gamma 5 u, that is always equal to u. So, you can always split it into two parts. The second thing that you check is that with this definition of UR and UL, whether you are adhering to your original definition of UR being eigenstate of gamma 5 with the eigenvalue of plus 1 unit. So, let us quickly do that exercise, right. So, you can see that gamma 5 UR is gamma 5 into half into gamma 5 U, and now multiply the gamma 5, bring it inside. So, this is gamma 5 and gamma 5 square. Now, you need to remind me what was the gamma 5 square, and we said that that is actually equal to 1. So, this is essentially half into gamma 5 plus 1 into u, and this quantity is nothing but PR into u, and that is nothing but UR itself. So, this is showing that UR is an eigenstate of gamma 5 with eigenvalue of plus 1. Similarly, you can show that gamma 5 when acts on UL, this is a trivial exercise, but let me do it a little. This is half into 1 minus gamma 5, that is the definition of PL, and this is going to give you, minus of half into 1 minus gamma 5 U, which is minus UL. Okay. So, similarly, you can also check that VR and VL are also the eigenstates of gamma 5. So, I can define, for example, VR and VL, which will also be, you can project the V into VR plus VL, where you define VR. Remember, for antiparticle, the definition slightly changes. This is consistent with all these definitions that we have done so far. So, VR is essentially PLV, which is half into 1 minus gamma 5 V, and VL is PRV, which is half into 1 plus gamma 5 V. And once again, with this you can check here that it is kind of obvious that gamma 5 VR will be actually minus VR, and similarly gamma 5 VL will be equal to plus VL, correct. So, this completes our definition of what we call the chiral states or the chiral projections obtained by these projection operators PR and PL. We can also see that PRUR will be what? PRUR, UR is PRU anyway, and PR square is PR, right. So, PRUR is essentially once again UR. PRUL, this is PRPLU. What was PRPL? This will actually annihilate. So, this is going to be 0. So, similarly, PRVR is going to be 0, and PRVL is going to give you PRV, which is actually VL. So, this also means that PR projects the right chiral particle and left chiral antiparticle states. So, this is how you can do, and similarly you can check for PL, PLUR is equal to 0, while PLUL is equal to UL, PLVR is equal to VR, and PLVL is equal to 0. That basically means that PL projects left chiral particle and right chiral antiparticle states, and this is something that you should check explicitly. So, therefore, we have sort of now gaining more and more insight about what is chirality, but I would like to now explain this a little more. And what we said is that the chiral states are nothing but the helicity eigenstates in ultra relativistic limit. But this raises a question that can I not define a relationship of between helicity and chirality, not exactly in the ultra relativistic limit, but when we are in the normal relativistic regime, right. I mean where I have E square equal to P square plus M square without any assumption. I do not need to drop M square here and so on and so forth. So, in that case, once again you let us remind the helicity state and see if we can write it in terms of the chiral states, because then it will be, the picture will be clear that how precisely the helicity states can be written in terms of the chiral states. Let us write the u up, and this is something that we actually saw right above, that this is C S e to the power I phi kappa C and kappa S e to the power I phi. I have devised a small notation kappa here, which was what? This is simply E by P plus M. Just for the sake of simplicity, we write it like this. Now, for example, what I would like to do, that I would like to take the projection operator PR on u up and see what exactly it does. So, what was PR? PR was half into 1 plus gamma 5 u up. And now, what I am going to do, that using the form of gamma 5 in the Dirac-Pauli representation which we found out, I am going to write this PR operator. So, this is half into this particular form, and u up is precisely this one. Now, if you do the matrix multiplication here, it turns out to be something very interesting. You find that this is coming up like C plus kappa C, S e to the power I phi plus kappa S e to the power I phi, once again C plus kappa C and S e to the power I phi plus kappa S e to the power I phi. Now, what is this? This is basically saying that this is actually half of 1 plus kappa into this n into C S e to the power I phi C S e to the power I phi. Now, this C S e to the power I phi C S e to the power I phi is nothing but precisely the helicity eigenstate in the ultra relativistic limit, which is nothing but the chiral eigenstate. So, I can simply say that PR u up is turning out to be half into 1 plus kappa into u r. And similarly, I am not doing this exercise here, but you should actually do it. It is not very difficult to do, but you have to do the matrix multiplication carefully to show that PL u up, this is actually coming out to be half into 1 minus kappa u l. Okay. Remember, the kappa is nothing but that factor of E by P plus M. Now, I can always say that u up, whatever the spin or states that is, u up is one of the helicity eigenstates that we are talking about. And so, u up can always be written in terms of the two different projections like PR u up plus PL u up, simply because of the fact that the PR plus PL is always equal to 0, right. So, I can always write it like PR u up plus PL u up, but the point is that PR u up can be written in terms of half into 1 plus kappa u r, while PL u up is half into 1 minus kappa u l. Now, this exercise you can do. So, this actually shows how the helicity eigenstates and the chiral eigenstates are actually related to each other. Now, this exercise I can also do for u down, v up and v down, and I urge you that you should all do this as your homework exercises. Okay. So, this is a very interesting story. I would like to also now remind you of something that we actually discussed in the beginning. We are writing the Dirac equation, and we said that we actually identified the probability density and probability current density associated with the Dirac equation to follow a continuity equation, as you could do it for the Schrodinger equation, as you could do it for the Klein-Gordon equation. Similarly, for the Dirac equation, we could actually devise a definition of rho and j, so that del rho del t plus divergence of j is equal to 0, and it turns out that the rho was psi dagger psi and j was defined as psi dagger alpha psi, where alpha was one of the matrices with which we actually wrote the Dirac Hamiltonian. Now, we could actually dress it up a little more to write it in a nicely covariant form and write it like del mu j mu equal to 0, where this j mu is a 4 current constituted of this rho and j, and we could write it in terms of the Dirac matrices. Now, before I write, if you remember what exactly was the form of j mu, you should tell before I write. This was something like psi bar gamma mu psi, right. So, this is exactly the form of J mu which was conserved, del mu J mu equal to 0 for the free Dirac equation. What was the definition of psi bar? Psi bar was defined as the adjoint spinor, and it was defined like psi dagger gamma 0, right. So, this is the definition of the adjoint spinor. Now, what I am going to do, that I am going to try and decompose this current which is psi bar gamma mu psi or J mu in terms of the chiral states, and let us see what we can do. The first thing that we have already seen, that psi is equal to psi L plus psi R, where this is PL psi plus PR psi, which is half of 1 minus gamma 5 psi plus half into 1 plus gamma 5 psi. So, this is something that we have already shown. Similarly, the adjoint spinors like psi bar, that can also be written in terms of psi L bar plus psi R bar. Now, what is psi L bar and what is psi R bar? So, that is the question, because psi L and psi R we have written, but psi L bar and psi R bar we have not written explicitly. So, let us see that. So, what was the definition of psi bar? Psi bar was defined, the adjoint spinor was defined as psi dagger gamma 0, correct? So, what should be the definition of psi L bar then? It should be defined as psi L dagger gamma 0. What is psi L? Psi L is simply PL psi. So, it will be PL psi whole dagger gamma 0. Now, when you take AB whole dagger, that will be B dagger A dagger, that is the matrix rule that we have learned. So, therefore, we say that this is psi dagger PL dagger gamma 0. Now, what is PL dagger? PL, you remember that PL was what? Half into 1 minus gamma 5. So, what will be PL dagger? PL dagger will be half into 1 minus gamma 5 dagger. Now, what was gamma 5 dagger? This was gamma 5. So, this remains the same. So, PL dagger remains PL. So, this is becomes psi dagger PL gamma 0. Now, however, gamma 0 gamma 5 is essentially minus gamma 5 gamma 0. So, this quantity like PL gamma 0 can always be written as gamma 0 PR, just because there is a negative sign which you actually obtain when you actually do this anti-commutation relation between gamma 0 and gamma 5. So, let us see it explicitly. So, suppose PL gamma 0 kya tha? PL gamma 0 will be written as half into 1 minus gamma 5 into gamma 0. Now, you can always write this to be half into gamma 0 into 1 plus gamma 5 using the anti-commutation relation, and you can simply say this is gamma 0 PR. Okay? Now, gamma 0 PR hone se kya hoga? That psi dagger gamma 0 once again could be called psi bar. So, psi bar PR. So, psi L bar is essentially psi bar PR, and similarly I can write psi R bar. Psi R bar kya hoga? Now, that will be psi bar PL, correct? So, this is how exactly we should write the adjoint spinor in terms of the projection operators. But remember, this whole exercise that we have done here is actually for the particle spinor. For antiparticle spinor, the definitions are little different. This is actually applicable for particle spinors. So, for antiparticle spinors, please do this exercise. Please do the same exercise for antiparticle spinors. All right. So, let us proceed with this. Let us assume that this psi and psi bar, these are actually the particle and their adjoint. Now, J mu is psi bar gamma mu psi. So, therefore, I say that psi bar is psi L bar plus psi R bar into gamma mu into psi L plus psi R. If I do the simple algebraic manipulation, this will have all the possible terms like psi L bar gamma mu psi L, psi L bar gamma mu psi R, psi R bar gamma mu psi L, and psi R bar gamma mu psi R. Now, let us look into this term like psi L bar gamma mu psi L. So, from the definition that we have found out that psi L bar is psi bar PR gamma mu, and then this will be psi L is PL psi. And from also this operation of gamma mu with PL and PR, just because of the anti-commutation, we say that okay, now if I want to take this gamma PR on the other side of gamma mu, क्या हो जाएगा, this will turn into PL. So essentially PR gamma mu becomes gamma mu PL, and we already had a PL there, and this is coming from the fact that PR gamma mu is equal to gamma mu PL. And on the other hand, PL square क्या है, PL square is PL itself. So this is like gamma mu PL psi. So this current looks like psi bar gamma mu PL psi. So this has a term, I mean if you just inflate this term a little, this looks interesting, that this is like psi bar gamma mu by 2 into 1 minus gamma 5 psi, right. So look into this current actually not only have psi bar gamma mu psi kind of a term, but it also has a psi bar gamma mu gamma 5 psi kind of a term, right. So that is interesting. So similarly, if you now want to do this exercise for psi L bar gamma mu psi r, so from this definition we know that this is becoming psi bar PR gamma mu, and this psi r is PR psi, and then PR can be brought on the other side of gamma mu and it becomes PL from the anti-commutation. So this is PL PR psi. Now PL PR is equal to 0. So this actually goes to 0. So therefore, out of these 4 different terms that we actually wrote in the chiral decomposition, there are only 2 terms which will be non-zero. Which will be there? Which is like psi L bar gamma mu psi L, the left chiral current so to say, and the right chiral current psi r bar gamma mu psi r. So these are the terms. So explicitly show what exactly this term will correspond to and how the other terms. So the way psi L bar gamma mu psi r is equal to 0, similarly psi r bar gamma mu psi L is equal to 0, and the other non-zero term is only this thing. So these 2 terms will be surviving, and so therefore you can conclude that in a vector current only the similar chirality combination actually retains, while the admixture of different chiral combinations that goes to 0. So this brings us to a short preamble of what we say, that in general there are different kind of bilinears that you can define with the Dirac fermion or Dirac spinors. In general these are written like psi bar capital gamma psi, where gamma can be 1. So you can have psi bar psi, which we usually call a scalar. Gamma can be a gamma mu, where you know this can be a psi bar. So this is what precisely we were talking about, psi bar gamma mu psi. I can also have just a psi bar gamma 5 psi. So psi bar gamma mu psi is called a vector. Psi bar gamma 5 psi is called a pseudo scalar. On the other hand, I can also have psi bar gamma mu gamma 5 psi, and that I can say it's a pseudo vector. And I can also have a sigma mu nu in between, which is nothing but I by 2 commutation of gamma nu, and this is a tensor. Okay? And why these are called pseudo psi bar gamma 5 psi and psi bar gamma mu gamma 5 psi as pseudo scalar and pseudo vector? This because of their parity transformation, they under parity they actually flip signs. So that's why they are called pseudo scalar and pseudo vector. So in the couple of minutes that is left, I would like to define what are the parity transformation properties on the Dirac fermions. So let's actually try to do that. So the first of all, what we say that what is a parity transformation? The parity transformation is defined by a mirror symmetry in the spatial coordinates. So basically x prime is equal to minus x, y prime is equal to minus y, z prime is equal to minus z. However, t prime remains t. So suppose if I then try to say that what happens if I do a parity transformation on the Dirac spinor. So suppose I consider that operator to be p, and the process of transforming psi to psi prime is an operation of having an operator p acting on it. What does it do? That it takes the psi from x, y, z, t to x prime, y prime, z prime and t prime, where x prime, y prime, z prime and t prime has this above kind of relation that you know. Now, I would also like to take you to this point that if you do a consecutive parity transformation, like suppose you go to psi prime and then operate parity once more on it, what will happen? That it will bring it back to its original place. So, therefore, p psi prime, which is p square psi, is equal to psi. That means that p square operator, if the parity operator is acting twice, that is nothing but the identity operator, so to say. Okay? Now, what is this parity operator which can be operational on this Dirac spinor is a question that we would like to ask. And in order to do that, what we have to remind ourselves is of the Dirac equation. So, what is the Dirac equation? Dirac equation is simply I gamma mu del mu minus m psi equal to 0. So, if you write it component wise, then you can dress it up further to write it like I gamma 1 del psi del x plus I gamma 2 del psi del y plus I gamma 3 del psi del z minus m psi is equal to minus I gamma 0 del psi del t. So, this is how you can inflate those term by term in terms of different mu equal to 0, 1, 2, 3 coordinates. Now, suppose I do a parity transformation on psi, which I said that I have now a psi prime which is a function of x prime, y prime, z prime and t prime, which is actually obtained by operating p on psi x, y, z, t. Okay. So, let us write it in the parity transform coordinate system. So, I say that this above equation turns into I gamma 1 del psi prime del x prime plus I gamma 2 del psi prime del y prime plus I gamma 3 del psi prime del z prime minus m psi prime is equal to minus I gamma 0 del psi prime del t prime, right. Now, I am going to use this points that psi prime is nothing but equal to p psi and x prime is equal to minus x, y prime equal to minus y and z prime equal to minus z with t prime remaining t. So, if you do that, this equation becomes minus I gamma 1 p del psi del x minus I gamma 2 p del psi del y minus I gamma 3 p del psi del z minus m p psi is equal to minus I gamma 0 p del psi del t. I am going to multiply from the left with a gamma 0. If I do that, then what happens? This equation becomes minus I gamma 0 gamma 1 p del psi del x minus I gamma 0 gamma 2 p del psi del y minus I gamma 0 gamma 3 p del psi del z minus m gamma 0 p psi is equal to minus I gamma 0 square p del psi del t. Now, you also remember that there is this anti-commutation relation between any gamma matrices like gamma 0 gamma k is equal to minus gamma k gamma 0 when k is not equal to 0 and gamma 0 square is also equal to 1 or the identity matrix basically. So, now what I can do that I can take this gamma 0 from left to right on the side of each of these gammas that we have. So, this then eats up this sign, and what I am obtaining here is that this is I gamma 1 gamma 0 gamma p del psi del x plus I gamma 2 gamma 0 p del psi del y I gamma 3 gamma 0 p del psi del z minus m gamma 0 p psi, and here this will be minus I gamma 0 p del psi del t. Now, if you look into this equation, this looks very much like the original Dirac equation which was written in untransformed coordinate system, and that resembles that equation if you just put this gamma 0 p is equal to 1. Now, you also say that we already know that p square must be equal to 1 or the identity matrix, because that is a parity transformation. So, parity transformation twice will bring you back to the same position. So, therefore, looking into these two things, I can simply say that I have the option of choosing the parity operator to be either gamma 0 or parity operator to be minus gamma 0 to act on the Dirac spinors. Usually, the convention is to set p is equal to gamma 0, because if you add this parity operator on u1 at rest once more, that u1 m0, then you see that this gives you u1. When you operate this once again at u2 m0, this is going to give you u2. That means these are even under parity for those which are the particle eigenstates, and on the other hand, if you add this parity on v1 and v2, this will give you minus v1 and minus v2, which are odd under parity. So, that is why we choose the convention of choosing parity transformation to be gamma 0. So, with this we are actually going to finish these lectures on the Dirac equations and its solutions, and in the process not only we have talked about the Dirac equation and its solutions, the energy eigenstates, the helicity eigenstates, the chirality, but we have also talked about some very interesting discrete symmetry transformation, the one which was the charge conjugation, from which you can go from one particle state to antiparticle state, and also we have obtained something like a parity transformation, under which the question is that we did the parity transformation and identified that what parity transformation on the Dirac spinor should be, and we argued that must be equal to gamma 0. So, with this I finish this lecture today. Thank you very much. So, I will see you in the next lecture. Thank you.